Cool. We might just get started. So hi everyone, welcome to the third installment of our academic series. Today we're incredibly delighted to host Professor Anna Paradowska with us. Firstly, Anna, thank you so much for taking the time to spend your evening with all of us today. And just a bit about Anna. Anna joined the University of Sydney at the end of 2019 as a professor in advanced structure materials. She currently collaborates on multiple national and international research and industry-focused projects involving the cross-correlation of neutron-based techniques and standards development for additive material manufacturing. Those joining will be happy to know that Anna works as a scientist, but is actually an engineer by heart and education. She has a PhD in mechanical engineering from Monash University and a Masters of Science degree in material science from Wrocław, I hope I'm saying that right, University of Technology in Poland. Anya has an extremely diverse and impressive portfolio, and who better to speak about it than Anna herself. So Anna, the stage is yours.
Thank you very much. I really appreciate it, Andrew. So I am really glad that I can share my passion for science at the large scale facility and showcase a little bit more how you in the future, if you wanted to do projects in collaboration with between Sydney and ANSTO, maybe could use this facility. And so as been told, I am a very enthusiastic engineer who work at the large scale facility. And, you know, I was the first engineer to be employed at the large scale facility in ICES. Normally, you know, physicists and chemists and scientists working on the beamlines. But when I finished my PhD, I was looking for something interesting. I was a user of large scale facility, but then I thought, okay, I will become an instrument scientist and I can collect that ring. So it was a unique position and a risk from my employees to actually employ just a graduate and also first female and the engineer. But I think it make a change for the whole system, because now as I come back to Australia and work for ANSTO, I have 3 other engineers working with me, and we wanted to have this more interaction. So you need physicists to build the facility, but you need an engineer to run it. So I think in this case, my biggest niche, I think, is that my first degree is a little bit on material science, so I can talk to the physicists, but my practical aspect of my work in mechanical engineering and civil engineering is that I can talk to the industry. You know, so the thing is, knowing these languages, these different approaches to things, really helped me build my facility, build my expertise, and build my network and find my own niche. So if you're interested to what I do also am a very transparent scientist, I would say, and I am using a social media quite a lot, because I think it's really important that besides communicating through the conventional channels like papers, we also communicating our science with general public and people who fund us, you know, in our case, the government in Canberra. So I do lots of posts on LinkedIn about the science we do at the large scale facility and about diversity and inclusion. That is very important for me, especially in the engineering space. So I don't know, not everybody knows, so you know, because you know that you're coming to the nuclear presentation, but actually Australia have a well-established nuclear capabilities for nearly 60 years, and we are in the suburban of ANSTO, and I will talk today a little bit about my research, but also introduce what other ANSTO aspects you can do, what other kind of research you can do at ANSTO, my two loves, which is residual stress and imaging. And I will give a case studies of how is that related, how the science on small angstrom level is related to large scale bridges and large scale infrastructure. So I think as our problems and manufacturing is developing, we also have to develop characterization tools. So I'm a characterization tool specialist, and my specialty is non-destructive testing. But I don't want to explain this, but it is another microscope. I'm just powered. But you know, the tools that I use, they are just powered by the nuclear reactor. But we're looking at the things on the very, very small scale, and we correlate them to the large scale infrastructure. So you can see even my facility is built like a heart. How can you not love it? So this is ANSTO. ANSTO is only 35 kilometers from the CBD. We have actually historically 3 reactors there. I did my MOAT is the first reactor ever built there, but doesn't exist anymore. Haifa is the reactor that I did my PhD on it, and then we have our new Opal reactor, modern reactor. It's only 11 years old, and is a very in the reactor age, that's a baby, you know. So what we can do in this facility is quite incredible. And I think it's so important that you at least come for a visit. And if you're interested, I will be very keen to host it and give you a VIP tour of our facility, because I think we can impress better if you see what we have on offer. So we are 20 megawatt open pool reactor. Why open pool? You know, you can isolate radiation with 20 millimeter of lead, 1 meter of concrete, or 6 meter of waters. We have the same shielding. So the fact that we have an open water reactor allows us to see through. Yeah, and it provides very good shielding, so we can operate around the reactor and also see, put things inside to irradiate safely and repeatedly. So we also have, as you can see, besides the reactor, lots of research facility, and I think that is actually the biggest advantage for us, because ANSTO is probably more known outside Australia than it is in Australia, that people don't even sometimes know that in Sydney there is a nuclear reactor. But people come from all around the world to do the science at our facility. I love my job because, you know, people come and for 3-4 days, and before they start annoying me, they're going home, you know, but they come with the fruits of their science for a short period of time to really do unique things. So what we have at ANSTO, we have this multi-purpose reactor. My facility, Australian Centre for Neutron Scattering, is directly attached to it, and we are like a neutron factory. We use neutron to do irradiation, imaging, diffraction, lots of different characterization methods. From we do food science, energy materials, we do construction materials, anything, electronics. Neutrons have a magnetic moments, and we can measure things in superconductors, and lots of variety of science. And I think the biggest advantage of ANSTO is also that we operate large infrastructure around Australia. So Australian synchrotron, for example, in Melbourne. So again, I don't have to say that the neutrons are in competition with X-ray. We complementary. And in my research, I use both. I use synchrotron and neutron facility. Besides that, we have a national deuteration facility, center for accelerators, and medical research. I think most of the Australians who knows ANSTO, they know that we produce nuclear medicine. 1 in 3 Australians will have to have a nuclear medicine rather for diagnostic or the treatment in their lifetime. So we don't have to justify our existence because we really, really need it. But besides that, we also have other businesses around nuclear space, and we provide advice to the government on all aspects of nuclear. So I am running industry engagement office at the ANSTO, but nobody on eBay is actually searching for neutrons. So how to sell scientific services to industry that is not knowing you exist, or they don't know how to use them. Yeah, so the thing is, it takes me quite a long time to figure out what my niche is and what my product is. And I don't sell people neutrons, I sell solutions. So I build a capability and expertise with my colleagues around the Center for Neutron Scattering to provide a solution for the industry. So what we do is characterization and process development. We do materials consulting, novel materials development, and structural analysis. And I think if you break that sort of barrier, then we're relevant to everybody. It doesn't matter in my industry partner produce electric cars or digging the mines. If he knows that we can help him in characterizing this product, I at least have a starting point for a conversation. I think my biggest problem is to explain it that we don't do rocket science only, because people think if you work at the nuclear reactor, that means you have to do some rocket science. We do, but a majority actually as an engineer, what I do is prototyping and production improvement. So we do work on these fundamental areas of superconducting or of magnetic properties, quantum computing. Yes, we do that, but in engineering space, in advanced manufacturing, mining and defense, we do product improvements, novel processes, repairs. We help in structural integrity of aging aircrafts, aging infrastructure, bridges. We developing novel manufacturing technology in 3D printing space to apply to the repairs. So what I'm trying to do is to help industry discover that we can do supply contribution to the knowledge across the full value chain. Yeah, so from the early research through prototyping and production, and the same for our academic user. So the beauty of the work we do is that it can be anything, really, from the early stage of fundamental study to really production. And I find this very exciting because I can help small and medium enterprises grow and grow with them. And I show you a couple of examples of this. So when I started my research 10 years ago, I arrived at ANSTO. We have 6 companies that never really pay us. Yeah, they just do research with us. But I think if you have a focus on solution, and majority of the companies you can see here, in welding and large scale manufacturing, is this is my area of expertise. But I think I just sort of knew what they require. So I don't experiment with my industry client. I experiment with my PhD students and my master's students and undergrad students. But what I sell to the industry is solution. And I think that is an important aspect, that, you know, that we can play in a lab for science, but if we want somebody to pay for it, we have to give them the measurements, and we have to give them opportunity to use this to enhance their performance or improve safety or reduce the cost. So when I talk to my clients, the CEOs, I'm not talking how the reactor works. I'm talking that I'm coming here to solve the problem that by improving efficiency, reducing the cost, and of course safety is our priority. But there is a lot of science for these things to happen, and I think that is an important thing in working in a large-scale facility, that our facilities have a direct impact on the industry around us. Okay, my children think I work in a zoo because all our instruments are named after the Australian animals. There is only one that is named Sika, that is not not Australian animal, but is a Taiwanese instrument built by the Taiwanese team. So we allow them to make the name that is relevant to them, and but it have to stick to our sort of zoo portfolio. We're building now a new instruments with the German team, and they will have then we will have a SPAT, which is a sparrow. And I hope we're going to grow a few more instruments that will be expanding our portfolio of the research and a portfolio of our research capability. But I will talk today about Covari, which is the strain scanner, and Dingo, which is our imaging beamline. So I'm a residual stress expert. Yes, so I measure stresses locked in within the components due to the manufacturing. And why this is important? Yeah, because it is important because those stresses, when you superimpose operational stresses, they can lead to fracture, stress corrosion, cracking, fatigue, and distortion. So when we, in the past, when people have a catastrophic failure, like we see over here, they will say, oh, that's residual stresses. Now they cannot say that, we can measure it. Yeah, we can use a nuclear reactor and we can measure these things fully non-destructively and assess if the residual stresses were the cause, or the cause was, for example, imperfection or some welding flaw or some overloading. But so in structure integrity analysis, we looking into failure assistance. We're looking into help our industry to find the solution why things are cracking and how to mitigate the stresses so this cracking will not occur. There are several ways to measure residual stresses. The non-destructive green on this graph are lab X-ray, synchrotron X-ray, and neutron diffraction. There are also some destructive methods that require cutting the specimen or drilling the hole or slitting. So it's generally industry and academia don't like to do destructive testing because you cannot repeat it. Yeah, so non-destructive technology allows you to repeat the measurements, and the beauty of neutron is that we cover nearly all of them. So we can cross-correlate neutron diffraction with other methods. So we are a great validation tool. And we've been around for more than 2 decades, so we already have a standard. So for nuclear application aerospace, residual stresses as parts of the structure integrity assessment. But what my role is actually breaking this technology to other industries, to civil structures, to pipeline industry, to railway structures, so that we can learn and enhance the technology, manufacturing technology in that space to take advantages of stress engineering. The general rule of thumb is that we wanted to measure residual stresses in as smallest area, as smallest spatial resolution as possible, and in thicker components, because larger the constraint condition, the larger the stresses. But we always have some limitations. So there is no ideal technique to measure things. There is a fit for purpose. Yeah. So one thing can measure a surface, one thing can measure subsurface and large components. So the beauty of neutrons is that we can measure large scale components, thick and fully non-destructively, and 3 directions. So stresses are 3-dimensional, especially if it is a pressure vessel or a rocket or an aircraft wing. They never as simple as tensile specimen on the uniaxial loading rig. Yeah. They are biaxial or triaxial. So understanding the stresses, if you understand the stresses, you will come up with the way to mitigate them and even improve performance. So as I mentioned before, this is our strain scanner, and we measure small things, you know, like 3D printed vessels or large component. Here I have this pipe that comes from the Cambridge TWI, the Welding Institute Cambridge, and is a 1 meter diameter and 1 meter length, 800 kilogram beast. This is the biggest component ever measured on the strain scanner. And I did try to measure that in Europe, but it was not possible because our reactor is the youngest and our instruments are the youngest. We learn from other people's experience. We everything is movable. We actually call the floor a dancing floor because all our apparatus is on the air pads, so we can mitigate and move beam stops and move our incident beam, and we can reconfigure the configuration for many different applications. So we can look from small components, nozzles, to archaeological objects or Japanese swords, to large-scale components like pressure vessels and big pipes. So there is a variety of opportunities for us to measure. So we're relatively fast. We have minimal preparation. We have to have a reference point. So that is a key. And we don't do spotty measurements. We can create full maps. And I think that's the biggest advantage. And you can repeat. If you make a mistake, you can do it again. And you can do it as a factor of multiple changes in the process production. So if it's heat treatment or other methods you apply to the manufacturing process, we can check that, or even simulate the processes. In bridge constructions, this is very important, and especially for bridges, columnar structures are key components, and residual stresses are very vital for performance of the lean steels and green steels. And we have here columnar structures for welded components for bridge application. Do you hear the echo? No.
No, it's all
So,
good.
okay, sorry. So I have it here, a distribution of residual stresses in the thin sections, a small column and large column. And we don't have measurements only at critical location like wet. We can measure all around it, and we can create maps with high resolution. So when you implement a new technology for civil application, this is critical, because these high strength steels that we're implementing in the bridges, they have different response due to the welding, and all the in-service stresses are superimposing on the residual stresses that already exist in the structures. And by knowing them correctly, we can change standards or update the standards to include this novel welding technology or novel steels in constructions to become more popular. On the other scope of our research is, for example, pipeline industry. So this is a hot tub, and this technology to welding this hot tub, it takes 24 hours and 6 welders. Yeah, so you can do it only once, right? You have to do it right the first time. So before you do this kind of repair or expansions of the pipeline, if you build a new suburbs, you build a bubble around it and then make a connection to the existing pipeline. So the industry have to train the welders to do that and come up with the novel technology to do that faster, safer, and more efficient with no defects. So we were helping the 2 clients in the space via the energy pipeline CRC projects to develop a novel welding technology by manipulating the sequence of the welds and mitigating the residual stresses from the critical location. So in welding, the critical location is the welding toe. That's where is a fusion line, and then you have this heat affected zone. That's where the crack, in service crack, fatigue crack, will start propagating. So by mitigating the weld sequence, we can move the high tensile stresses from this critical region to the middle. In welds is usually stronger, and we can it is easier for us to repair it than the sort of like a casting. I'm sorry, I'm just going to go back to this. So what we did here is that we measure stresses in the components, and we validate it by finite element modeling. I mean, that is important. Not every component, this hot tub weighs 3 tons, so there was no chance I could measure it, but we could make a mock-up that is very similar to what we do, what they will experience in the field, and we can assess it. And of course, we assess it before they come to us. They measure the microstructure, they measure the hardness, that they require all the mechanical properties. But if they still have a problem, or they wanted to have a reassurance, they will come to us to make sure that the process that are implementing in this manufacturing of this hot tub, it is they can make an engineering choice on the safety of that novel welding technology. And it's been great, because I think it helps us develop the trust, help us change the current standards, and implement this technology to pipeline industry that normally will probably didn't know what to do it. But we give them more facts about the process, that it's easier for the structural engineer on the pipeline to assess if it is safe to operate. The another example is here. This is a research with the DSTG group, and particularly here landing gear for the helicopter. And I think it's really cool, because it showcased the fact that we can measure things on the small scale. And here we have a cladding tensile specimen that are also not only cladded, but they are deep surface rolled. So this is like a hammering technique that is implemented to improve performance by introducing compressive residual stress. Under compressive residual stress, crack cannot grow. Yeah, so you can see here we have a coating. After the cladding repair, already we have a really nice compressive stresses in this area of the coating. However, just on the interface between the substrate and the coatings, the stresses are 0. The most defects, Murphy's law, that the defects will always occur in the place you don't want it, which is interface. So actually, but introducing the deep surface rolling, we introduce more compressive stress, and we pass this interface. So that means that even if we have a defect in this area, the crack will not grow. And we could prove it, because I could measure residual stresses in situ as well, and we prove it that actually the cladded specimens with the deep surface rolling, they perform better than the original, the raw material. You know, so you can do stress engineering on really interesting way, that you can improve performance of highly fatigued material by implementing compressive residual stresses into the surface. So tensile stresses, cracks propagates. Compressive stresses, cracks can be resisted. In civil structure, this is a bit tricky, because all bridges, large structures, are designed in that they loaded in the compression. So compressive residual stresses are not as desirable, actually, you know. So every industry have their own challenges, and I think it's so important that by understanding the stresses, we can help industry and academics to develop the technology that is suited for purpose. Here I have another example from in fatigue space. So this is part of the cruciform specimen from the oil industry. Yes, so offshore rigs, because of the waves and high winds, they constantly being subject to fatigue loading. And by implementing also ultrasonic pinning, we are able to enhance the performance, like in the previous example of complex oil rig structures, you know, to being pinned, introducing compressive residual stresses, enhancing performance, day fatigue performance by a factor of 10, you know, so which is huge for repair industry. But you can really help strategize your maintenance strategies for oil industry. And not only oil, you know, it's all other industry taking a full advantages, car industry, aircraft industries, wherever you have a fatigue as a primary force of loading, you wanted to introduce compressive residual stresses because they will act into your advantage. Another big things that Neutron can do, we can measure things when they're changing. So we can do the things in situ. So here's one of my PhD student helping me to measure the stresses, stress relaxation during the heat treatment. So one of the methods of reducing stresses in civil structures as well as pressure vessels is heat treatment. Yeah, so you heat treatment the weld to 600 degrees and hold it there for an hour, and the residual stresses will not be reduced to zero, but significantly reduced. And we can measure that stress relaxation, and we call that primary creep and a secondary creep in situ when it is happening. For example, in my second example, I have a super alloy. Yeah, so this is an aircraft component, another PhD student. This is collaboration between 3 large-scale facility. We're trying to prove to Rolls-Royce and other nuclear company that we can measure repetitively at different large-scale facility. And what we're doing here is like here in super alloys, the heat treatment is not 1 hour, it is 6 to 12 hours. So every hour is expensive. Yeah, so you wanted to make sure that you achieve the desirable residual stress relaxation in as shortest time as possible. And by observing how that change when you manipulate the temperature, you can reduce the cost, minimize the risk, and improve efficiency. Another aspects of interesting work that we are doing that is relevant to structure is using laser technology, for example, for forming. And I have a projects with Harriet University in the past for shipbuilding. Yeah, normally we use laser to weld or cut, but you can also use it for forming, and especially for large-scale structures. And for civil engineers, I think is also quite an important aspect, you know, because we now shaping, we are more adventurous. Not everything have to be straight, bulky lines. It can actually be, you know, exciting and curvy. So I think laser forming have a huge potential in civil industry, and we can measure residual stresses in those components and help engineers understand how they will superimpose in the operational stresses and how to mitigate them if necessary to improve performance. Another aspect of the work I'm really do, so my background is welding. I specialize in a welding of pressure vessels. But when the VAM technology, weld arc additive manufacturing, came into play a couple of years ago, I was very excited because this is just a welding on speed. So here we're using conventional arc welding processes to 3D print. I love 3D printing on laser beds and conventional laser techniques, but they cannot build or compete for large structures. Weld arc additive manufacturing can compete, and I think it will have huge potential application in civil structures in the future, because we could build them to reduce the carbonized civil structures on site. So we don't have to bring this large scale complex component into the construction site. We could build these things on site. So here I have a landing gear and work I was doing with one of my PhD students, that we can measure the stresses in various types, various stages of the manufacturing process, as manufacture, after machining, and then compare them and mitigate them further if necessary with heat treatment or pinning or other methods. So I think there is a lot of potential for this technology. Here are some comparisons of the residual stresses on the laser bed. I mean, Sydney Manufacturing Hub at University of Sydney have access now to some really exciting technology for laser beds, and I'm also developing new facilities that I would like to share with you for large-scale manufacturing. So here we're developing with Professor Kim Rasmussen large understanding of the how VAM technology can be used in large scale manufacturing. And I build a setup to do this kind of things with my technicians on our instruments. So what we do is actually measuring the strain buildup when we welding, when we depositing the subsequent layers, which gives the opportunity for manufacturing industry to understand the stresses with complexity. So before we measure it before and after, yeah, now we can measuring when it's happening. And another interesting project that we are developing now is with my postdoc Halsey and the team at ANSTO. We're building a setup for direct powder laser deposition. So not a laser bed, but you have nozzles to deposit powder inside the beam, and you can do cladding, you can do 3D printing this way. And I think it will be the first facility, powder facility in the world. And I think it's exciting because it will open avenues not to only measure strain and stresses, but also to look at the defects development. Yeah, so all these processes are only as good as their quality. So we need to understand the stresses, and we need to understand the defects that are forming. So, and that brings me to the next beamline that we have it at ANSTO, which is called DINGO. So here, DINGO is a hole to the reactor, because you need to have maximum of neutrons, as you know, and the radiation there is the largest, the highest in the whole our experimental hole. So what we use here is this is an imaging technique. You put the objects that you wanted to investigate, and then you can do radiography, like you have a Röntgen when you have a broken bone, or you can make multiple images when you rotate the samples, and then you can reconstruct this into create full tomographies of complex shapes and interesting components to see how to understand. So lucky for me, we operate the synchrotron and neutron facility, and we have imaging beamlines on both. You can see that there is a big difference between the image for neutrons and the image for synchrotron. So in X-rays, when you larger the atomic number, the more difficult is to penetrate, because in synchrotron facilities, the X-rays interacts with the electrons. Neutron facility, neutrons are big, so they go straight to the nucleus. Yeah. So the thing is that we can see different things, and it's very random for us. So we can see polymeric structures, we can see composite materials, and so the techniques are complementary. We see different things, but by investigate those things with a different method, we can combine and fully understand the object. And I'm going to show you some videos here of complex shapes components. I'm just gonna try to, they will run in the background. So for example, 3D printed components often have a porosity, and this porosity can be determinantal to the structure. Defects can start growing out. It's important to understand the density of the 3D printed components. As you can see here, you know, that we have a very good quality at the start of the build, but not as really good quality in the end of the build. But often industry will apply post-processing, like heaping. So they will put it in the furnace, applied pressure, and this pores can be closed through the processing, but you need to make sure that this actually happens. So we often help our industry client and our scientific researchers to see the samples before and after processing, if those all pores are able to close. In turbines, the only method that you can repetitively apply to investigate corrosion in turbine is neutron, because neutrons can see full, not only metallic structures, but also organic residue and corrosion. So you can have a full tomography of a complex shapes, and then go in stages and try to find the critical locations and cooling in the cooling channels of the turbine blades. This is very important, and neutron radiography and neutron imaging is one of the characterization tools that that they use around the world. Here we have another examples of 3D printed components, and this project I have with NASA to develop the standards for 3D printing components. And when they first approach us, they approached me because I'm a residual stress expert, yeah. But I was saying, okay, we have some other amazing tools, and we would like to showcase, because we can see images, and they say, okay, we do that with X-ray. We don't need neutrons. Neutrons too expensive. However, instead of measure one component at the time, I can put 5 of them at the time and have very comparable resolution. And for visibility perspective, is a no-brainer for the engineers that he wanted to see 5 at the same time. So, and actually the cost is not that expensive, because I use the same time for 5 as they used to make them independently, you know. So I think it's so important that there is a technique for purpose, but there are certain advantages for neutrons that are complementary for conventional X-ray radiography. Here's another example. This is a Anya's crown. No, this is a part of the rocket, and it's an interesting thing. So the same things. It comes to me to measure residual stresses, but before we measure the residual stresses, I'm very interested in developing the link for a tomography-driven diffraction. So in tomography-driven diffraction, you first take the image of the objects that is three-dimensionally complex, and then you put it. I have a virtual instrument of Covari, and I can locate the measurements points where I wanted to measure, and manipulate on the robot to put it to the specific location. But when I did the tomography, I realized, oh, what is this red thing? It shouldn't be there. Is there 2 materials? And they just testing me to see if I can see it. And actually, what it happens to be is just the residue from cutting. So, you know, like when they cut the specimen, usually they pull the water to cool it down. It's electric discharge machine, and there's lots of dirt in it. So the supportive structures in this build is very porous. And supportive structure for engineers is not of interest. It's just there to make the build happen quicker. Yeah. So you will not consider supportive structures being an issue, but because it affects balance, the weight is not uniformly distributed. If there is any residue in the supportive structures, the rocket, instead of going straight, it goes the wrong way. And the tolerance on in space industry are really tight. So, you know, the 3D, they didn't understand why the problem occurring, you know, why they don't have a uniform distributions. And we were, even before we start measuring the residual stresses, we help them find out that they have a residue in the supportive structures, and by implementing ultrasonic pinning, they could easily get rid of it. We also help them to find defects. So defects, porosity, see if they are in the critical locations, and help them mitigate. So I think combination of imaging and stress analysis provide a huge potential for the manufacturing industry, and also dimensional stability. So just to sort of summarize, in the end, I think neutron research facility, especially imaging and residual stress facilities, provide a huge potential for welding industry across many sectors: civil, pipelines, aircraft, nuclear, and they make the technology and research in science as well as in engineering and on industry stage very interesting, because we are able to make a direct impact on economy, reliability, and safety. There is a lot of science put into it in the background, but you don't need to know all the details, you know, to drive the car. Yeah. So I think it's so important that we teach our students and we teach the next generation of scientists and engineers that the tools like that are available, and you can come and use it. And I hope that if you go into the industry after you graduate, and you become like our ambassador for this industry. You know, like if anybody will need tomography or we need neutron stress measurements, we are just available to anyone. We are open to academia and open to industry, and the best way for us to access that is actually by educating the students who are going to go places. And I'm so excited that I have a chance and opportunity to talk to you. And if you ever need an expert, nuclear expert, we have plenty of them, 1,200 of them at ANSTO. Thank you very much.
Wow, thank you so much, Anna. It's crazy to see how useful neutrons are, and it's also very clear how passionate you are about this topic of matter. Now we might just move on to the Q&A section. I'm just gonna share my screen to show the Slido questions. Are you able to see my screen now?
Yes.
Oh, perfect. So the first question here, I think, is quite interesting. What has changed the most in the industry of material science / engineering while you've been studying / working in the field?
Okay, that's a very good question. So I've been in this materials research for 15 years. The science did not change. The engineering did not change. The speed changed, and automation. Yeah, so I think in material science characterization, we do now have robots to do the things we used to do by hands. And in production lines, we now have an autonomous robotic system that do that much more reliable and more efficient. But the beauty of this is that my original background in engineering still allows me to apply the same principles to those processes. To those characterization processes and to the manufacturing processes.
Wow, that's great. Thank you so much. And the next question here is a bit more personal. I recall you saying that initially in your career, you were the first female employee in this field. As an extension to that, did you face any challenges as a woman in STEM?
I mean, it is a lonely place for a female. But I think it's changing, you know, like, okay, I've been here longer than you, than the females that probably in the audience, but it's still really, really relevant. Look at that us, yeah. At civil engineering, we only have 2 female professors at this stage. So we're working on it. We really wanted to make change. I have 2 brothers, and I thought, you know, engineering is for everybody, you know. So I think I grow up in a sense that I like to make my hands dirty and try to fix things. And I think when I start working as an engineer, I only realize that there is a strong need for inclusion. Like, I'm not better than any of my colleagues, male colleagues, opposite. I may be weaker in some other points, but I bring diversity and I bring different perception, you know, and I think it's proven in literature and in really big projects that diverse team perform better. And, you know, it's so important for for a multidisciplinary team, and that we develop this inclusive leadership and inclusive teamwork environment. I think I've been first every time. I'm the first research at Monash to work as a welder. I'm the first one at INSEE, the first one. I never really knew that I'm the first woman. I just thought that everybody can do it, you know. But I think not every woman will have that sort of pushy power to move it. That I think that's why the industry need to be more and science need to be more inclusive to allow other females to come along, because I really the females that comes behind me, oh my gosh, get ready, they are amazing. You know, and I have many of female PhD students and undergrad students that are better than me and will be better than me, and 10 years from now they will be leading the industry. So even though I have my little challenges, I'm very excited about the future of engineering, because there is many amazing females in the pipeline that will be more visible in the next few years.
A great answer, and it's great to see how you're forming the path for other female people in STEM. So yeah, it's great to see that. And just diving a bit into your engineering experience, because most of the people here are, I'm assuming, like engineering students. Can you tell us a little bit about your engineering experience?
I have a materials background in material science and engineering and monitoring system. Yeah, and then I work as a physicist, and then I work as a mechanical engineer. Before I started my PhD, I worked for 4 or 5 different companies. I designed surfboards, cutting machines, architectural glazing. I get bored very quickly, as you can see. so I find a place at university, because finally I'm faced in so many challenges at the same at large-scale facility, that the dynamic of changing projects and products is happening very quickly. I find, you know, being a foreigner, arriving, actually my first experience as an engineer was in Australia. Yeah, I finished my master's degree in Poland, and I came as a fresh student studying. I studied diploma of business because it was cheaper than studying English. But I was trying to find my ground here. And I will say to every engineer that's trying to do that and trying to find a job, is just you have to get yourself open to whatever opportunity comes. You cannot be picky. You know, like for me, I try different things and try to find my strengths and work on my weaknesses. I think to every engineers that are doing through the pipeline now, I will say 3 things. Like, if I will do it again, I will learn how to code, I will learn how to draw, and I will figure out how to communicate my research or my ideas, you know, with some sort of social platform. And I think I did that slowly through my career. But you are in such an early stage of your career, that's the time to focus on these 3 things. Because I think future of manufacturing and future of civil engineering, assessment, structure integrity, will be in AI, machine learning. And, you know, so as soon as you start, get a little bit of grip in modeling and dealing with the big data, it will really help you. And I think if you wanted to have career, communication is not just for social science. You will have to communicate with your clients, with your boss, with your colleagues. So as soon as you get yourself, it's a skill that nobody's, when I actually come here, I was very shy and I didn't speak English. It was very difficult for me to communicate, but you learn how to communicate, and you get better with experience. So I think that's how I will phrase this, that I have lots of different little jobs here and there, and I learn what I like and I learn what I don't like. and it's important to have those experience on the way. So I would say take internships, ask your a lecturer that if you're interested in this, if there is a summer project or a winter project that you wanted to do. I did that during my master, and I sort of figure out what I don't like. I didn't know yet that I like welding, but I just sort of think just by trying different things, I was able to get where I am, and it wasn't a straight path. And I think from my experience now, 20 years finishing my master, my first undergrad degrees, be patient. You know, because often when we're young and excited, we wanted to be retired by 30. And what are you going to do for the rest of your life? You know, actually, I'm inspired by people who are start patenting after they're 60, you know, because finally they have time to do these innovative studies. They have the experience, you know, and I think I'm not the most patient woman, but I'm learning. But I think it's so important to learn as much as yourself, invest in yourself. If the job you don't like it, you know, gives you some experience, it's still an important step in your career, because they all builds you up.
Definitely. Wow, great answer. Yeah, speaking of learning, that just shows how much we can learn from you. And just as an extension to that question, you mentioned how, you know, you really like a dynamic environment where you keep having the opportunity to do new things, explore new things. Is that what initially drew you to the research side of this field of materials?
I think first I wanted to be a teacher because that was the only
Oh,
woman
okay.
career, only the job I saw smart women you know, sort of doing it. I think for me, when I was growing up, it changed my dad have a business, and we constantly things were breaking, and it was a large buses, so that we were constantly repairing. So I like fixing things, you know, and I like feeling needed. So I found it that kind of career path, fixing and teaching, I would say, and constant learning. Like I have done double degree. I'm addicted to learning, and was sort of important for me that I wanted to have a job when I grow with, and I find it that across you know, like I started, my first job was in the restaurant and waitressing, for example. I still think it was a valuable step for me because I need to talk to anybody, you know, like
Definitely.
learned how to talk to different people, and I think it gives me that confidence to do it. And I remember when I have my first job as an engineer, I came to for the interview, and the guy who interviewed me told me, "You don't know how to sell yourself. Like, you already have the highest degree in this company, but you don't know nothing." and he was saying to me, I was remembering that I was like, I have this 5 years of experience, like being a undergrad, and how nobody ever taught me that I need to sell myself. I thought I have to show my degree, and this is what I done. And people will automatically knew that I'm good. But no, you have to find your niche, and you have to find the way, your way, how you make the contribution to the company, to your environment, impact on your research, on your students. And I think I like my job because this is constantly changing. And I watch my students growing, my PhD students running a company. Some of them are CEOs and more money than me. But it's exciting for me to be a part of their journey, and that is very stimulating for me. Like I think I like helping people
Definitely.
getting where they want to go.
Definitely. Wow, thank you so much for that answer. And thank you so much for taking the time. We really understand how busy you are and how many things you've got going on. So we really appreciate the time you took this evening. And on behalf of everyone here, thank you so much. And could I just ask everyone joining us today to just turn on their camera so we can take a quick picture for marketing, please?
Visibility.
Definitely.
I just wanted to say that, I'm quite approachable. If you have any further questions or you wanted to have a discussion, quiet discussion or something, send me email. And I'm here to help. I wanted to know you in some way or another, and I hope to see you coming for undergrad thesis or master and do exciting project with us.
Definitely. Thank you so much, Anna. And to all those joining us today, thank you so much once again. I just want to inform you of the events coming up. We've got the Multicultural Day coming up, and the Women in Industry panel and the Trivia Night. And we also have our White Card Day coming up. So don't forget to sign up for that to get your white cards. And that's a wrap for tonight. Thank you so much, everyone. And thank you, Anna.
Thank you. I'm just trying to wave. Cheerio.
Bye.
Thank you very much.
Bye. Thank you.
Thanks, Anna. That was great.
Thank you. Thank you. Oh, I'm so nervous, but I'm glad that it